So let's begin with some field and take a prime, which is not equal to the characteristic of the field. And for n greater than or equal to 0, let this HNF mu L tensor n be the nth Galois cohomology group with values in this the mu L tensor, mu L tensor, mu L n times. And by Hilbert 90, we get this f star mod f star square power n. These are the nth powers of the field, and this quotient group is isomorphic with H1F mu L. It follows from the Hilbert 90 that H1F GM is trivial. So given element A in F star, so consider this class of A in F star mod F star power L and take its image in this H1F mu L. That's denoted by bracket A. Now take some finitely many elements A1, A2, AN in the field. Then, so we have each AI in H1, and then the cup product gives an element in the HN. So we denote by this A1 dot AN. Now an element of HN is called a symbol if it is equal to this cup product of AIs for some AIs in F star. So for example, let's assume that the field contains L roots of unity, and let's look at n equal to 2. So this is just a Brauer group, and this corresponds to the so-called cyclic algebras. And if L is 2, these are the famous quaternion algebras. So theorem of Wygotsky, of course, for n equal to 2 and L equal to 2, this is a famous theorem of Suslin, says that every element in H2F mu L is tensor product of quaternion algebras. And for general L, it's the theorem of Mercury of Suslin. And for more general field and NLN, so this theorem of Wygotsky says that every element in HNF mu L tensor n is a sum of symbols. I mean, this is a map okay, so for the n equal to 2, so this says the Brauer group, the two torsion of the Brauer group is generated by quaternion algebras. That is a famous theorem of Mercury. And so take any element alpha in Hn, F mu L tensor n. Then by theorem of Wygotsky, we know that it is a sum of symbols. And let's define the symbol length of alpha. It's the smallest positive integer m, such that alpha can be written as sum of m symbols in this Hn. So once again, if you look at two torsion element in the Brauer group, so we know that it is a tensor product of quaternion algebras. And what is the least number of quaternion algebras we need to write that as a tensor product of quaternion algebras in the Brauer group. So that's the symbol length. And we say that a field is NL bounded if there exists a positive integer n such that the symbol length of every element of Hn is bounded by this n. So that every element in Hn is sum of at most is capital N symbols. Okay, let's look at quickly some examples. If F is algebraically closed, there is nothing because all these cohomological groups are trivial. And if it's a finite field, we know that at least 2 these are trivial. So H1 is everything in the symbol in H1 by definition. If it's a local field, we know that this Hn is 0 for n greater than or equal to 3, and every element in H2 F mu L tensor is a symbol. So once again, if the mu L is in F, so this is a H2 F mu L is a L torsion of the Brauer group, and it says that every central symbol algebra of L torsion is a cyclic algebra. And if it's a global field, then every element in Hn is a symbol. So in fact, if F has no real orderings, then Hn is 0 for n greater than or equal to 3, and every element in H2 is a symbol. So all these fields are like NL bounded for every n and every L. Now question is, so start with any field k and a prime not equal to the characteristic k and take n bigger than or equal to 2. Suppose there exists an integer n such that every element in Hn has symbol length bounded by n. So can you say the same thing for kt, or more general if function fields of curves over k? So in other words, does the NL boundedness of k implies the NL boundedness of kt, or more generally the function fields of curves over k? Of course, this is very general question and it's quite open for general fields. We have no idea how to go about for general fields. But we consider fields of arithmetic interest.
I have a question.
Yeah.
What about just finite extension issues for your question?
Yeah, finite extension also we don't know in general. So if suppose k is some field k is NL bonded, is every finite extension is k NL bonded? No, we don't know that.
Okay, thank you.
Yeah, actually, if the KT is NL bonded, then one can show that every finite extension of K is NL bonded. So maybe should I put that as a more general question, that suppose every finite extension of K is NL bonded, does it imply that KT is NL bonded? So we consider fields of arithmetic interest. So in fact, say raise the following question. So let K be a periodic field and F equal to KT is every element in H3 of mu2 tensor P is a symbol. So that means every element of H, so the symbol length is 1. So say raise this question in connection with Cayley algebras, because we know that for any field, the set of isomorphism classes of Cayley algebras over F is in bijection with a subset of H3 of mu consisting of symbols. So in other words, if we take a simply connected split group of type G2, then the Rost invariant map is injective and every element in the image is a symbol and every symbol is in the image. So there is a bijection between this H1FG and the set of symbols in H3 of mu2 that are called H3 decomposable elements. So the say raise question, if the say question has an affirmative answer, then the Rost invariant map is a bijection for a periodic field K, because every element in H3 KT is a symbol we are saying. So therefore this is bijection. In fact, it gives the following nice description of Cayley algebras. That's why Sayre asked this question. So let K be a periodic field and P the set of close points of P1K. And for any X in P, let kappa X be the residue field at X. Let CP be the set of functions F from the set of close points to Z mod to Z with finite support. That means only finitely many F of X are non-zero, and such that the sum of all is F of X where X is in P is 0. Then we have this H3. So we have H3 kappa X mu2 tensor 2 is Z mod 2 because the kappa X is the residue field at a close point. So this is a finite extension of this periodic field. So therefore this is just Z mod 2Z. And we have the following exact sequence because of this KT. So this is, and where this map, the H3 KT to the H2 kappa X is a residue map, and this H2 kappa X to H2K is a co-restriction. So it's a residue map for all this, and these are induced by the co-restriction. So take the sum of all the co-restrictions. So this leads to the identification of H3K2 to tensor 3 with CP, because each of this H2 kappa X is Z mod 2 and this also Z mod 2. So this exact sequence immediately gives the identification of H3 with CP. So let's look at the Brauer group, so which is more important to us. For a field F, let Brauer F denote the Brauer group of central simple algebras over F. And for L greater than equal to 2, let L Brauer F denote the L torsion subgroup of this. And we have this the L torsion of the Brauer group of F isomorphic to the H2 F mu L. So suppose mu L is contained in F, then mu L tensor N is same as mu L for all N. Thus we have this, the L torsion of the Brauer group of F is same thing as H2 of F mu L tensor 2. Now it's known that if you have 2L, if F is 2L bounded, if and only if there exists an integer n such that for every alpha in the 2 torsional group of F, the index of alpha divides 2 power n. Of course, one way is easy, because if it is 2L bounded, that means every element in the Brauer group of F is tensor product of some m cyclic algebras, and each cyclic algebra has index at most L. So therefore, the tensor product has index 2 power. Sorry, there is a mistake here. This is not 2. This is L power n. So if you take an element in the Brauer group of L torsional Brauer group of L. Suppose that 2L, it is 2L bonded. That means this element alpha in the L torsional Brauer group of F is tensor product of some finitely many cyclic algebras, some bounded number. So therefore the index is at most 2 power n. And for the converse, of course, then you have to look at this generic algebras, and we know that every central simple algebra, L torsion central simple algebra, is a product of cyclic algebras, and look at the generic algebra, and then you specialize that, and then you get. So the if index alpha divides 2 power n, then you can get that it's 2L bounded using generic algebras. But more generally, so for any alpha in Hn, let index of alpha be the GCD of the degrees of finite separable extension with the image of alpha in HNL mu L tensor n is 0. So this is same as the index of a central simple algebra, what we know in general. So we can define for any element like this. The theorem of Krashen for general L and Saltman for L equal to 2. So let F be a field and L a prime not equal to characteristic of F, and let any n greater than equal to 2. Suppose that for every m greater than equal to 1, there exists an integer nm such that for every finite extension with degree less than equal to m, and for every element beta in hi of L, the index of beta is at most nm. So it's not only for the F, so it's for finite extensions. Also it's bounded, but this bond depends on the degree of the extension. Then F is Ln bounded. So if you know that the indices are bounded, then we can show that it is Ln bounded. So not only for the Brauer group, so it's true for any Hn. Okay, so that is one of the reasons why we're interested in bonding the indices to get about NL boundedness. So one way to show Ln boundedness is of a field is to bond the indices of elements over all finite extensions. Okay, so in this direction, the first theorem is due to Saltman. Let K be a periodic field and n co-prime to P. Let F be the function field of a curve over K. Then every element in n torsional group of F has index at most n squared. So this will show that this F is n2 bounded. Sorry, this is n2 bounded for Ln bounded for L2 bounded for all primes. So, but suppose you take n equal to 2. So the 2 torsional group of F has index at most 4. So by theorem of Albert, so any central simple 2 torsion central simple algebra of index at most 4 is a tensor product of 2 quaternions. So the symbol length is at most 2. But for higher primes, if you know the index is L square, we cannot say that it is a tensor product of 2 cyclic algebras in general. But there is some bond. But now let's see what happens. So the beautiful idea of Saltman splitting ramification and classification of close points on the ramification locus in the proof of the above theorem led to many other interesting results. So one of them is the following thing. So let K be a periodic field and L is co-prime to P. Suppose that mu L is contained in K. Let F be the function field of a curve over K. So then, as I said, if L is 2, so it's already due to theorem of, it follows from Albert and the Saltman theorem that everything is a sum of 2 symbols for L equal to 2, but for any L, so we have this following theorem, say that anything is a sum of at most 2 symbols. So it just doesn't follow from the period index points, so we need more things. So we need this classification of points, what Saltman calls as hot points, cold points, chilly points, and so on. So he gives a criteria when an algebra is a cyclic algebra for prime degree algebras or prime torsion algebras. So using that, we proved this theorem. So therefore, so it shows that this field F, the L2 bound of this is 2. Now, so for the same field, so it's a periodic field and L is co-prime to P. Suppose that mu L is contained in K and take the function field of a curve over K. Then every element in S3 of mu L tensor 3 is a symbol. So this answer the question of Sayre in affirmative. So Sayre asked only for L equal to 2, but we proved for any L. And of course, we use this L is not equal to P. So what happens L equal to 2? Of course, later on, so we also proved about the U invariant, but there we assume L is not equal to, P is not equal to 2. But by a theorem of Heath-Brown and Leap, so the U invariant is 8 for all function fields of curves or periodic fields. So in general, in particular, if you take L equal to 2, the U invariant is 8 implies everything in S3 is a symbol. S3F mu L, mu2 tensor 3. So therefore, even for L equal 2 and P equal to 2 also, this is true. Okay, so now what about the number field case? So let K be a number field and F the function field of a curve over K. And given any alpha 1 alpha to alpha m, then there exists F in F star and beta is in H2, such that alpha is F dot beta I for all I. So that means if you go to square root of or Lth root of F, sorry, this is L and 2 got mixed up. So this is only for 2 at that time, we proved only for L equal to 2. So if you go to square root of F, so any of the given finitely many alpha i's, we can find some F so that when you go to square root of F, all these alpha i's becomes trivial. So therefore each alpha is F dot beta I for all I. So this is analogous to the Tate's lemma where for number fields, given some finitely many elements in the H2, we can find a common slot. And we're doing here, we did the same for elements of H3, so we can find a common slot. Of course, this doesn't prove anything about the symbol length because we don't know anything about the beta i's. So in particular, if F is 2-2 bounded, that means each beta is some bounded, sum of bounded symbols, then this will show that F is 3-2 bounded. But is the F is 2-2 bounded? That's still an open question. And in some other direction, if you take any Ci field and suppose mu L is contained in F, then there exists a positive integer n which depends only on I, such that every element in H2 is a sum of at most n symbols. So that means the 2L symbol length, this field is 2L bounded. Okay, this is our main theorem. So take any global field and F the function field of a curve over K. Let L be a prime not equal to characteristic of F. So because the global field, so it could be positive characteristics. So I want. So for the number field case, so there's no condition L. And suppose that the mu L is contained in K. And if L equal to 2, assume that K has no real orderings. So in the number field case, so we want to assume that it is totally imaginary. Then every element in S3F mu L tensor 3 is a symbol. Actually, yeah.
I have a question about the function field over a p-adic field. Is L a prime there, or is it just anything which is co-prime to P?
No, it's a prime. For the symbol, yeah, when we show it's everything in S3 is a symbol, so we look at only for primes.
Okay, thanks.
And we also assume that L is not equal to P there. Okay, so it's an open question whether F is 2L bounded. So this theorem shows that this is 3L bounded, but we don't know whether it's 2L bounded or not. Okay, so now we give some applications of our main theorem before giving an idea of the proof. So let F be any field of characteristic not equal to 2. Let WF be the Witt ring of quadratic forms over F. And so this is the, so you take isomorphism class of quadratic forms and then the orthogonal sum and the tensor product, and you take the Witt authentic group out of that. And modulo the hyperbolic forms. So in other words, the WF is in bijection with set of all anisotropic quadratic forms over F. Isomorphism classes of anisotropic quadratic forms over F. And inside that, you have this fundamental ideal consisting of even rank forms or even dimensional forms. And for n greater than or equal to n, let this INF is the nth power of this ideal. And given any AIs in F star, so let this A1, A2, N is the tensor product of this binary quadratic forms. And this is called n-fold Pfister form. And it is easy to see that the INF is generated by this n-fold Pfister forms. And so we have this WF mod IF is just the dimension. So it just gives the dimension mod 2 gives an isomorphism. And then the discriminant gives an isomorphism from to the F star mod F star square. So the discriminant is the sign determinant. And then I2F mod I3F, the Clifford invariant is an isomorphism with H2. This is the theorem of Merkurov. And for any INF mod IN plus 1F is isomorphic to HN. This is the theorem of Orlov, Ishik, and Wygotsky. And here the map, so the given an n-fold Pfister form in IN, so it goes to the symbol A1.A2.AN. That's the map there. Okay, so F is a function field of a curve or a total imaginable field, then every element in I3 is represented by a Pfister form. So our main theorem gives the following corollary that, so that means, in other words, if you take a quadratic form which represents a class in I3, then the anisotropic part must be at most 8. So any 9-dimensional form or 10-dimensional form in I3 has to be isotropic. So since the cohomological dimension of F is 3, because we are taking curve over a total imaginable field, the total imaginable fields have cohomological dimension 2. So the function field has cohomological dimension 3. So we have this H4 is trivial, and therefore the I4 is 0, and the I3 is isomorphic to H3, because I3 mod I4 is H3, but I4 is 0. Actually, this is already theorem due to Arizan, Elman, Jacob. It's proved, I think, in 80s, where they prove it for any cohomological dimension 3 fields. Or you can use this Orlov-Ishik-Wygotsky theorem, which is true for any field. And the result follows from our main theorem, because everything in H3 is a symbol. Therefore, everything in I3 comes from a symbol here. So it's a n-fold Pfister form, a 3-fold Pfister form. Okay, now again go to the general field, characteristic not 2. And the invariant of F is defined as the maximum of the dimensions of anisotropic quadratic forms over F. And the conjecture is that if F is a function field of a curve or a total imaginable field, then the U invariant is 8. Of course, we don't even know whether this U invariant is finite for this field. So far from knowing anything about this conjecture. But on the other hand, if you look at some special forms, so let F be the function field of a curve or a total imaginable field, and you take a quadratic form over F of dimension at least 5, and take some element in lambda in F star and look at this quadratic form, which is 10-dimensional, at least 10-dimensional, because Q has at least 5-dimensional, and this tensor code gives at least 10-dimensional, and this form is isotropic. Of course, if the U invariant is 8, this has to be isotropic. But without knowing the U invariant, using our main theorem, we want to show that this Q tensor 1 minus lambda is isotropic. So let's quickly go through the proof. So without loss of generality, we can assume the dimension is 5, because we can get our, so take any 5-dimensional form of this Q, and if that tensor this is isotropic, then the Q tensor 1 minus lambda is isotropic. So we can stick to dimension of 5. And again, some quadratic form is isotropic if and only if any scalar times that, any non-zero scalar times that is isotropic. So by scaling, so you can write this Q as some minus A minus B, AB. So you look at the first 3-dimensional form and take the determinant of those 3-dimensional form and multiply by that. Then you can write like this. So the first 3-dimensional form has determinant 1 and some CD. So this for some A, B, C, D. So you can write like this. Up to scaling, any 5-dimensional form looks like this. There is nothing special about this. Okay, now we consider this Q prime. So given this 5-dimensional form, so we have this 6-dimensional form, which is the Albert form, associated Albert form, and you tensor with 1 minus lambda. And this Albert form is in I2, and this 1 minus lambda is in I. So therefore, the tensor property is in I3. So the Q prime is in I3. And anything in I3 is a 3-fold Pfister form. So Q prime is represented by 3-fold form. But actually, the dimension of Q prime is 12-dimensional, but it is represented by 8-dimensional quadratic form in the Witt group. But on the other hand, the Q prime is also, when you go to the square root of lambda, so the 1 minus lambda becomes hyperbolic. So anything tensor with that is hyperbolic. So the Q prime tensor f of square root of lambda is hyperbolic. So we know that you can take any threefold Pfister form, or more generally any n-fold Pfister form. If it is hyperbolic over a square root of some lambda, then you can write that as lambda comma some mu prime, or in general mu1, mu2, mu n minus 1 for any n-fold Pfister form. So because it's a threefold Pfister form and it's hyperbolic over this, so we can write q prime as this threefold Pfister form lambda mu prime for some mu prime in F. So since I for F is 0, so the q prime is in I3. So the 1 minus or 1 plus 1 comma CD tensor q prime is hyperbolic because this is in I4 and I4 is 0. So it is hyperbolic. So therefore you can q prime, any scalar is a similarity factor for q prime. So you can write q prime as minus CD times 1 minus lambda tensor 1 minus mu tensor 1 minus mu prime. So this without this minus CD, this is a q prime. And anything is a similarity factor for q prime because q prime is in I3 and I4 is trivial. So therefore we have this. Thus, so if you look at this q tensor 1 minus d, so this is, so the q prime is, so the first, this 5-dimensional form in q prime is q. So the difference between q tensor 1 minus lambda and q prime tensor 1 minus lambda is this minus CD times 1 minus lambda. So you just subtract that, then you get, so the q tensor 1 minus lambda will be just CD of 1 minus lambda tensor mu prime mu prime. Because this minus CD 1 minus lambda 10 times 1, so that goes away. So what you have is just this one. This is the width group, so they are equal in the width group. And on the left hand side, so the q tensor 1 minus lambda is 10-dimensional, and the right hand side is 6-dimensional because it's 2-dimensional tensor 3-dimensional, so 6-dimensional. So in the width group, a 10-dimensional form is equivalent to 6-dimensional form in the width group. That means this 10-dimensional form has to be isotropic. So this implies that this is isotropic. Okay, so note that as conjectured, if mu f is 8, then all 10-dimensional forms are isotropic. So there's nothing special about this q tensor 1 minus lambda, and every element in I3 is a threefold Pfister form. So thus we see the above corollaries as a strong evidence to our conjecture. Of course, here in this theorem, we didn't use much except that I4 is 0 and everything in I3 is a symbol. And for any field where I3, everything in I3 is a symbol and I4 is 0, the same proof goes through, and you can say that q tensor 1 minus lambda is isotropic. But there are many fields with I3 0, everything in I3 is a symbol, but I4 is 0, and we don't know about the U invariant. Okay, so now we give another application to zero cycles. So for a variety over a field K, let the Chow 0x denote the Chow group of zero cycles on X. Now suppose that K is a number field and X a variety over K. And if X is a curve, then a theorem of Morderweil asserts that the Chow 0x is finitely generated. This is classical theorem. And for dimension 2, one knows that the Chow 0 of X is finitely generated. Follows from the results of Merkurov-Suslin and Koletilin. Okay, what about higher dimensional varieties? It's an open question where this is finitely generated. And in fact, it's a conjecture due to many people. So that Chow 0x is finitely generated for any variety or a number field. So we should look at some class of varieties, namely quadratic fibrations. So what does that mean? So let's start with any field of characteristic not 2. And take a smooth projective geometrical integral curve for this K. And let pi from X to C be an admissible quadratic fibration. So what does it? So first of all, quadratic fibration means all the fibers are given by some quadrics. There is some technical condition admissible. So we'll not go into details of those things. Now let pi lower star be the induced homomorphism on the Chow group level. And let Chow 0 of X over C is the kernel of pi star. And for example, we stick to number fields. So we know that the Chaugier of C is finitely generated. So to know about the Chaugier of X, so it's enough to study the Chaugier of X or C. So that's why we're interested in this kernel. And Koletila and Scoraboto identified this group with a certain subquotient of Kc star. And let's explain what it is. So let Q be a quadratic form over Kc, defining the generic fiber of this. So this is a quadratic fibration. So each fiber is a quadratic, and look at the generic fiber. So that given by some quadratic form over Kc. And let NQ of Kc be the subgroup of Kc star consisting of products of even number of values of Q over Kc. So in other words, NQ of Kc consisting of product of so the elements of the form Q of V1 tensor Q of V times Q of V2 dot Q of V2n. So even number of values. Okay, then the theorem of Koletila and Scoraboto, which says that the group Chaugier of X over C is isomorphic to a subgroup of Kc star mod K star NQ Kc. In fact, what is the image of this? So they give some explicit description of the group of the image. So which is locally some unit times some value of this K star NQ Kc, but we don't need right now for our discussion. So that's why I didn't write it here. But there's an explicit description of the image of this Chaugier of X over C, in this case is star mod K star mod NQ Kc. Now let's go back to number field, and C is a smooth projective geometrical integral curve, and take an admissible quadratic fibration. And see that, of course, the dimension has to be at least 2, and if X is dimension 2, then we know already it's finitely generated. So suppose the dimension of X is 3, then Koletila and Scoraboto proved that this is the kernel is finite. Before that, okay, let me say that here, sorry, so you take an element of Kc star, so the squares are, we can show that it's in NQ Kc. So this is a 2 torsion group. So therefore it's Chaugier of X is finitely generated if and only if this is a finite group. So we're going to show, so it's in fact finite whenever it's finitely generated. So the Koletila and Scoraboto, when the dimension is 3, they proved that this is finite except one small case, which we completed that case, Formula and myself. So when the dimension of X is 3, so this is always finite. So in particular, the Chaugier of X is finitely generated. Okay, so now the corollary of our main theorem is that, so go to the same situation, totally imaginary number field, and see a smooth projective geometrical integral curve, and pi from X to C an admissible quadratic fibration, and suppose that the dimension of X is at least 4, then the Chaugier of X over Z is 0. So in particular, the Chaugier of X is finitely generated. So the kernel is not only finite, so we prove that it is 0. And this is what the Koletila and Scoraboto, they conjectured in that paper. And it just follows from the fact that once you know the U invariant is 8, it's immediate. But let's see otherwise how we apply our main theorem or crawl it to our main theorem. So take the quadratic form over Kc, define the generic fiber, and take a lambda in Kc star. Now the Kc, the K is, this is capital K. The capital K is a totally amenable field. And this is a function field of a curve. So therefore, this Q tensor 1 minus lambda is isotropic over this function field. That's what we proved in the previous corollary. So this is isotropic. So what does that mean? So that shows that the lambda, so this form is Q minus lambda Q. So there are some vectors V1, V2. So the Q of V1 minus lambda times Q of V2 is 0. So from that, you get that lambda is Q of V1 into Q of V2 inverse. But then we can show that it's product of 2 values. So hence lambda is a product of 2 values of Q over Kc, and therefore the Kc star is actually equal to NQ Kc. So that's the reason why we don't need to know what is the image of this here, because we are showing that Kc star is equal to NQ Kc. So therefore the whole quotient itself is trivial. So we don't care what is the image of the subgroup. So therefore the Chaugier of X over C is 0. So that completes our application part. And so again, so what we used is only the Q tensor 1 minus lambda is isotropic, and one expected like that the U invariant is 8. So that's the reason why Koletila and Scoraboto said that this has to be trivial. Okay, now, so we'll give an idea of the proof of our main theorem. Before that, we recall a result of Kato. Let K be a number field and R the ring of integers. And take F the function field of a curve over K. Then there is a regular proper integral two-dimensional scheme X to spec R with function field F. This is the resolution of singularities of two-dimensional schemes. And for a codimension 1 point, so that gives a, take the residue field and Vx associated discrete violation on F. So note that the residue field is a global field. So in fact, either a finite field, finite extension of this or number field K, or a function field of a curve or a finite field. So both cases can occur. And in the case of, if it is a number, if it is a finite extension of K, of course we have residue maps because of characteristic 0, the residue field. But if it is a function field of a curve or a finite field, and this finite field could be of any characteristic, so that's the reason we don't have in general residue maps, but Kato defined a residue homomorphism in this case. So the H3F mu L tensor 2 to the H2 kappa X Z mod L Z1. Note that if the characteristic of kappa X is L, then H2 kappa X is not the usual Galois cohomology, but it's defined using Dirac complex. So this is not the usual mu L, because in characteristic L, there's no mu L, right? So we have to look at a different group here, and then we have to look at this Galois cohomology of that. But however, so in both the characteristics, so the H2 of kappa X Z mod LG is isomorphic to the L torsion of the Brauer of kappa X. So therefore, actually, so we have residues from H3 to the L torsion of the Brauer group. So now if you take a close point, then look at the residue field. So this is going to be always a finite field. And since kappa X is a global field, and if P is in the closure of X, then we have a residue map from H2 kappa X to H1. So on the Brauer group level, for any global field, there are residue maps, right? And that's a class field theory. So we have these residue maps. And then Kato proved the following is an exact sequence. So from H3 to the direct sum of H2s, we're at codimension 1 point. So this is the residue map. And each kappa X is a global field. So we have the residue maps to the H1 kappa P. So take this direct sum. So this is an exact sequence. Actually, okay, so in particular, if you look at the H3 NR, the unramified cohomology, which is precisely the intersection of all these kernels, so this is a 0. The unramified cohomology is 0. Actually, in the proof, we don't really the exactness at the middle. In a way, yeah.
I mean H3 and the delta X is on H3F mu L tensor 2.
Oh, yeah, right. Thank you. This is H3. Yeah, right. So what we're going to prove, use that only this H3 unramified is triggered. So the injectivity here is what we're going to use. And in fact, we give a different proof for the exactness at the middle. So now let's come back to our main theorem, which we want to give a proof. So this is our main theorem. So we start with a global field, and F is a function field of a curve over K, and L is a prime not equal to the characteristic of F. And suppose that mu L is contained in K, and if L equal to 2, assume that K has no real orderings. Then every element in H3F mu L tensor 3 is a symbol. Okay, so this is our main theorem. So let's see how we see it. So since mu L is contained here, so we identify mu L tensor 3 with mu L. And hence we have identification of this. So we'll keep changing mu L tensor 3, mu L tensor 2. So we keep using both of them. So start with an element in H3F mu L tensor 2. Take the ramification of alpha to be all those elements such that the delta X is non-zero. So the residue is non-zero. And this is a finite set. It's well known, and it's called the ramification locus of alpha. Now, again, this is a two-dimensional scheme, so we can keep blowing up, and given any divisor, we can make it in good shape. That means it's a union of regular curves with normal crossings always. So what we do is first replace given this X by a sequence of blowups and assume that the ramification locus and the support of L, because L is our prime and L is not a unit on this scheme, right? Because this were global in the number field case especially. So we assume that our scheme X has this property, the ramification locus and the support of X. L is a unit of regular curves with normal cross X. Now further, we may assume that Ci intersection Cj for I not equal to j has at most one closed point. Again, if they meet at 2 points, you blow up 1 point, and then you get an exceptional curve. So we get one more curve, and they meet only at most on 1 point. So take beta I to be the residue of this alpha, so which is an element in H2 of kappa Ci. And as we said before, so this is the L torsion of the Brauer group of this residue field. And since each kappa Ci is a global field, so every element in this is a cyclic algebra, as we already said before. So therefore, we can write this as some Li over kappa Ci sigma I Bi for some cyclic extension, Li of kappa Ci of some degree L, and sigma I is generator of the Gala group, and some Bi in the kappa Ci star. Okay, now suppose the characteristic of the residue field is not L, and because we are assuming the mu L is contained in K, so this Li is given by some L root of Ai, the Kumar theory. And if the characteristic is L, because this is a cyclic extension of degree L, so it's given by some Artin-Schreier extension. So it's of the form kappa Ci x power L minus x plus A for some A. So in either cases, so we define this, we denote this beta I by this algebra A comma Bi. So this is, though we have put a different square bracket here, round bracket here. So in the characteristic not equal to L, this is the usual round bracket A comma Bi, usual cyclic algebra. And in the characteristic L case, so this cyclic extension is given by this Artin-Schreier extension. Okay, now, so what we do is, so our goal is to show that given, so this alpha is a symbol. So what we do is, so we produce some symbol such that the alpha minus that symbol is unramified, and use Carter's result to show that it's equal to that symbol. So we need to find 3 elements. So we are looking at H3, so the symbol, so we have to find 3 elements. So first look at this Ai, Bis, which are given in kappa Ci. So there are elements in kappa Ci. Now using class field theory, so we choose A, so this Ai, Bis are not uniquely defined because the algebra, so we are looking at the algebra beta I. So we have plenty of choices to make this Ai, beta I. So using class field theory, we choose this Ai, Bi with some off-a-dozen nice properties. So I'm not going to list right now. And one of the property asserts that the AIP, so the P is a close point of Ci. So the AIP means the AI is regular at P, and AIP is its value in the residue field for the at P and C. So look at this AIJ, so AIJ, and they should agree at for all P in the Ci intersection Cj, and similarly the Bi and Bj. Of course, if you take arbitrary choice, it won't work, but then you have to. So the Ci intersection Cj is a finite set. So we can make always some suitable choice at this finitely many close points such that this happens. And because of this Ai equal to this and this, so using some trick of Saltman, this allows us to choose some elements in F. So because you look at for example, the semi-local ring at all these close points, that's a 2-dimensional local ring on the scheme X. And then, so on the A mod, so look at each Ci corresponds to a prime ideal and go to the mod prime ideal, and we are given elements in the A mod, let's call it A mod Ci again, and such that they agree at the maximal ideals. So then one can lift it to get into the semi-local ring. So we choose some element GH in F such that the G of Ci. So what is G of Ci? So that means G is regular at this codimension one, this curve Ci, and its image in the residue field is Ai. And similarly for H. Further, we choose such GH satisfying almost a dozen nice properties. So again, this G and H are not arbitrary choices with this, but we need some more almost a dozen nice properties. Okay, so I'll come to that soon. But okay, so what we do with this? Okay, now once we choose this G and H, as I said before, so take beta to be G dot H. This is an element in H2 FMUL. And here, of course, one of the thing is, so we are trying to lift this G and the AIs and BIs. So let's talk about the lifting AI. So we're getting some G with this property. Actually, I didn't write complete details here, but see, because it's two different characteristics. One is sometimes the kappa CI could be characteristic L. So in that case, we are looking at the Artin-Schneider extension. And sometimes if the kappa characteristic of kappa CI is not equal to L, there we are looking at the Kummer extension. So we have to balance these two. So we have to lift it suitably. Okay, so now so take this beta to be this with the GH satisfying those dozen properties. So first we show that alpha is fx dot beta in the completion of f at all codimension 1 points of x. And then we show that there is some f such that alpha minus f dot g dot h is the difference is unramified. So when the difference is unramified, by result of Pareto, it follows that alpha is f dot g dot h. So this is a symbol. So as I said, we don't use the full exactness of the Pareto. Actually, start with any element in the middle, which goes to 0. So here we have some given only finitely many non-zero elements. So we call that support. So, and then you do the same thing exactly what we explained without talking about an element here. You can do this, all those things. And then one can show that there is an element, there is a symbol here which maps to this. So in particular, we're giving alternative proof that it's exact in the middle. And it also shows that it's a symbol. Okay, so that is roughly the idea of the proof. But then I said half a dozen nice properties and almost a dozen nice properties. So what are they? How do they look like? Okay, so now by blowing up X, so we further assume the ramification of alpha and the support of L is looks like that C1, C2, CR, as we said before already. But then we choose some in between CR1 such that the first the CIs don't intersect among themselves and the remaining CIs don't intersect among themselves. So you can separate them. So if you take any scheme and then you each intersection point, you blow up each intersection point, then you get the exceptional curve. You put all the exceptional curves at one side and the strict transform on the other sides, then that has this property. So this always can be done. Now let P be a finite set of closed points of this Ci containing all the Ci intersections Cj for I not equal to j and at least one point from each Ci. Now then there exists Ai, Bi and kappa Ci such that, so these are the half a dozen properties. So the residue of the beta I is this. So okay, what is beta I? Beta is the central simple algebras for kappa Ci. And if P is in the Ci, so that gives a discrete violation. So has a residue. Again, the residue field could be characteristic L. So that's why I wrote the square bracket this. So this is either Artin-Schneider extension. And if the residue field is not equal to characteristic, then this is the usual Kummer extension. And this is for the first CIs where 1 less than equal to I less than equal to R. And for the remaining CIs, it's the inverse because we want some balance. And at the intersection points, if P is in this finitely many points, which is not in the intersection, then we want this to be a trivial extension. So either trivial Artin-Schneider extension or trivial Kummer extension. And for every P, so P is a closed point of Ci, so it gives a discrete valuation on kappa Ci. So, but this P could be on two different CIs, so that's why I said PPI. So the P is in Ci, so this is a discrete valuation on kappa Ci at P. The valuation of all this Bi should be 1 for all at this finitely many closed points for the first Ci, 1 less than equal to I less than equal to R1. And the remaining I's, it should be L minus 1. See, when I'm looking like Lth power classes, so this is like the valuation of this should be like -1 if you look at mod L. But I want it to be regular. So I don't want to take the valuation to be -1. So I want a regular element. So that's why I put L minus 1. And finally, all these valuations should be sufficiently large, but not at these finitely many points, but there are some other chosen finitely many close points, which depends on these AIs. And at all those finitely many close points, I want this to be sufficiently large. And all these things can be achieved. Just take my word, because I can't explain all those things now. And once we have all these half a dozen properties, then we want to see what are the dozen properties. So given alpha in S3, so choose a model and GH in F star satisfying the following things. So the take beta is GH, G comma H. So again, the ramification of alpha is CIs, where CIs are regular irreducible curves with normal crossings. So here I'm not assuming that they are, okay, sorry. So the regular and normal crossings. So the ramification of beta is DIs are regular curves with normal crossings, and the DIs are not equal to CJ for all IJ. And I'm not saying that the DIs and CIs are in normal crossings. And if DI intersection DJ is empty for some 1 less than equal to I less than equal to M and M plus 1 less than equal to J less than equal to M. So if P is in any of this DI intersection DJ, then the characteristic of kappa P is not equal to L. So that's how this M is chosen. So the first few of them are characteristic L and the remaining are not equal to L. And there are no Chili loops. This is a Saltman classification of this nodal points for beta on X. And the delta Ci alpha is a specialization of beta at Ci. The beta is algebra on the function field. And so the beta is regular at Ci, and the specialization is algebra, and that should be the residue. And there's one more condition about the Ci intersection Dj. They should be empty for all the J less than equal to M and for all I. And we have one more condition of these intersections. And there is one more this. And finally, we have, and there's one more here. And there's one more. So one needs to achieve all these things. Okay, now the general result is that if you take any alpha and GH with beta equal to this, and if alpha, beta, and this X, the scheme X, all this, the triple satisfies all these conditions, then one can show that alpha equal to F dot beta. And therefore, and we show that that can be achieved, and then that shows that alpha is a symbol. Thank you.
Okay, thank you. Questions, comments? So you can use the chat if you want.
So do you expect every element in H3 a symbol if it has orderings?
I'm not sure. Sometimes I think, and sometimes I don't expect. Still, I'm in there.
Okay.
So today I say no. Tomorrow I don't know.
Other questions?
I had a comment at some point. You said that, did I hear that you said that if you take a surface of a number field, the Char group of 0 cycles is finitely iterated?
Yeah.
No, we have something about the torsion, not about Char group.
Oh, sorry,
itself.
only torsion. Yeah.
Okay.
Sorry.
I mean, for instance, yeah, if you take a case-free surface, for instance, we have no idea.
Yeah, only for the torsion.
Okay, thanks. I have a question, but I will say maybe later. So.
Is there a conjectural statement as to when every element in HN is a symbol for for higher n?
Yeah, so if you take a variety of dimension n over a member field and look at hn plus 2, and it should be a symbol. And for dimension equal to 1, that's because we proved that, and it should be true in general for any dimension.
Okay, so here is my question. So it seems to me that you did not use, this Kato local global principle, right?
No, we do is the kernel is trivial. The H3 unramified is trivial.
No, but the fact that H3 Q of T or Q of your curves inject in the H3 of the completions.
Yeah, we do use that. That's equivalent to the unramified trivial, right?
Okay. So okay. No, because I was thinking, maybe your result could explain this local global principle. But,
No. So I said that in the middle, the exactness in the middle, we didn't use.
Okay, good. Thank you. Okay, so no other question. No
Maybe
other
you could
comment?
you could tell us instead of taking something over a number field, if you take something over a function between one variable or a finite field, is the situation different?
No, it also works there. Yeah, I said any global field. Any global field, I said. No?
Any global field, okay. But for the question was Stein was asking, nothing better is known in a higher degree for varieties of higher dimension.
Or the positive characteristic global fields.
Yeah, if you take a a variety of a finite field,
finite field,
and you look at the right dimension for the cohomology, it's just given by one symbol or not?
For L equal to 2, yes, because of the U invariant. So they're L equal to 2 because of U invariant. Everything is a symbol in the top cohomology, non-zero cohomology. But for general L, I don't think it's known.
Okay.
So maybe last questions. Okay. So we thank the speaker